My talk is about entropy inequalities and applications to quantum field theory. So I will start describing what is entanglement entropy in quantum field theory. We usually call entanglement entropy to the entanglement entropy for a special partition of the Hilbert space, which is related to the regions. So we take a region, we trace the global state over the degrees of freedom outside this region, and take the von Neumann entropy of the reduced density matrix in the region. We also use the same name, entanglement entropy, for the entropy in this region, for example, for a thermal state where technically it's not entanglement entropy, but so more precisely, we are thinking in the entropy of a state in a region, which, so it's just the entropy in a volume. In the case of the vacuum state, for example, it measures the entropy in the vacuum fluctuations in this region. As quantum field theories have many degrees of freedom, have ultraviolet degrees of freedom, then this quantity turns out to be divergent, and the divergence come from the ultraviolet modes around the surface that make entanglement between the inside and outside. So one has, in general, an expression of this form, completely general expression in any dimensions, where we have divergent terms. This epsilon here is a short distance cutoff. It starts with an area term, and then we have a sort of other subleading divergences, eventually a logarithmic term, and some finite part. This area term, in fact, was the reason why this quantity was first proposed in the 80s and the 90s, in order to explain the entropy of, to give an explanation, a statistical explanation of the entropy of black holes, where because of the area dependence, in order to make this thing more precise, one has to renormalize this quantity in the Newton constant to give the Bekenstein-Hawking entropy. This expression in quantum field theory cannot be renormalized. We don't have the Newton constant if we take out gravity. So all these terms here are not important in quantum field theory. They are dependent on the cutoff. But there are many other quantities that one can think about in this expression. The coefficient of the logarithmic term. We know this is related to anomalies. Also, this finite quantity here, if we work enough to extract the universal parts, contains, for example, the usual volume increasing thermal entropy, and many other things, for example, topological entanglement entropy in topological theories. And, for example, one can extract some information from the correlation function of the theory also from this term, finite term. But, of course, these universal terms get contaminated with the cutoff dependence terms, so one has to do some special construction because one cannot renormalize the entanglement entropy in order to extract the universal parts. And this was already proposed in '94 in this early paper by Kahn and Wilczek, where they, in the conclusion of this paper, they say, well, there are many physical quantities that are relevant that can be extracted, for example, thinking in taking two states in the same region, and then one can subtract this entanglement entropy to get final results. Or, for example, consider a vacuum state and several different regions and making combination of entanglement entropy to obtain final results. Well, my talk is about, can be divided somehow in applications, it's about applications of entropy inequalities to these universal terms, and can be divided according to these ideas. One can take, for example, two states in one region, and one can then use this quantity. It's not exactly an entanglement entropy, but we will see the relation with entropy. This quantity is dependent of the two states reduced to the same region, and it's called relative entropy. And it is known that it's always positive and increasing with the region size. And this has led to the proof of several things, the entropy bounds. For example, we have a proof of Bekenstein bound using this, the positivity of relative entropy. And we have also a proof of Boso bound. This is a recent paper with Rafael Busso, Zachary Fisher, and Juan Maldacena. We have heard about that this morning. And there is also a proof of the generalized second law in the weak gravity limit by Aaron Wall in 2011. On the other hand, if we take vacuum state and several regions, one can make combinations and use this other inequality, which is called strong subadditivity, that has this particular geometric form for the entanglement entropy of regions. And with this, one can prove C theorems in 2 and 3 dimensions. This is a work with Marina Huerta, 2004 and 2012. So I have to say that these properties and these quantities were known very long time ago by people working in information theory, and the monotonicity of relative entropy and strong subadditivity are somehow the deepest known properties of the entropy up to now, and they are related to each other, so they are the same kind of a property. So I will talk about Bekenstein bound and the C theorems, and the proofs of these things are very, very simple, so I can explain the main features in the next few minutes. So let us start with Bekenstein bound. This was proposed by Bekenstein in 1981, doing this thought experiment with black holes. We take a large black hole with a small object outside, very near the horizon, and then we release this object and it crosses the horizon and disappears behind the black hole. So the initial entropy is the entropy of the object plus the initial area of the black hole, and the final entropy is the final area of the black hole. So using the generalized second law, one can see that this quantity has to be smaller than this quantity. On the other hand, Einstein equations relate the variation of the area of the black hole with the energy of the object that crosses the horizon. At the end, we get this inequality that is the entropy is less than 2 pi, the size of the object, times energy. This is a Bekenstein universal bound on entropy. And it has the interesting feature that it doesn't, even if it comes from black holes, it doesn't depend on the Newton constant. So one can think to test this bound or even to prove it in flat space. And it raises the question of whether this is a new constraint coming from the thermodynamics of black holes to flat space physics. So people have started to test this bound, and immediately it turned out that this raises several puzzles, this inequality. For example, what is the meaning of R here? If we have a quantum system, it cannot be really, this R is not completely well defined. It has always some tails outside some regions. So maybe this implies that one has to use boundary conditions to define the object in a specific region. In that case, it means that this bound depends also on some external element that is these boundary conditions. Another question was the entropy. We know the localized entropy is divergent, so what is the meaning of this equation if this is divergent, right? A different kind of problem is the species problem. We can think we have a theory we, for example, can satisfy this bound, but if we replicate the theory in a non-interacting way, we can produce states with constant energy, but where the entropy is increasing, logarithmically with the number of species because of the higher volume of space available. So eventually, for large n, this quantity will be bigger than this one. Another problem of this inequality, as is written here, is that the energy we know is positive, but localizes in some region, it can take negative values in quantum field theory. So this quantity can be negative, but on the other hand, quantum entropy is always a positive quantity. So in order to solve these problems, one can think including the quantum effects in this derivation in the original thought experiment by Bekenstein. Let us simplify the problem. We put some object, and here is a half space, so this is a Rindler horizon. And the experiment is just to put the object crossing the horizon. So the entropy before it crosses the horizon and after the crossing the horizon includes the entanglement entropy of vacuum in the region. So the final state doesn't have zero entropy, so it has the entropy of vacuum. And the relevant quantity in the Bekenstein experiment is, in fact, the difference of these two quantities. So, and in particular, the divergences will cancel in this combination. On the right-hand side of the inequality, we have 2 pi Re, and this can be replaced by the integral of the distance of the to the Rindler horizon times the energy density. And this is in fact the quantity that appears in the Bekenstein original derivation, because this is the quantity that gives the variation of the area of the black hole, which is related to killing energy, and near the horizon, the killing energy rises in this way. So really, the Bekenstein bound writes in this way. We can say that this is a quantum expression of Bekenstein bound. But then, the bound in this way already solves all the puzzles we have talked about. For example, what is the meaning of R? This is the product of ER, which is well defined through this expression. And it makes sense even if the object is not completely localized. It has some tails, the wave function outside the Rindler space. So it does imply boundary conditions. No, it does not. And in fact, it's important here we use entanglement entropy, because entanglement entropy is defined by a trace of degrees of freedom. So there is no boundary condition in this formula. No external element to the theory. So the entanglement entropy is divergent, but now we have this subtraction, so one can see that ultraviolet entanglement entropy from the vacuum that is present in both of these terms is cancelled. What happens if we increase the number of species? Well, the entropy will increase even at constant energy, but the vacuum entropy in the same region will also increase, and at the end, it will saturate. This was the result by Marov, Minik, and Ross. What happens with this quantity can be negative, the energy can be negative, but now we have a difference of entropies in this side of the equation, and this can also be negative. So all the elements are there. This is perfectly well defined. This is perfectly well defined quantities, so one can try to prove this bound. But in order to do that, we cannot escape to have some relation between energy and entropy. And this is already given by this universal result in quantum field theory, that the density matrix in half space is an exponential of this quantity, which is in fact is half of the boost generator. And this pre-established relation has been proved by Bisogniano-Wichmann in '75 in axiomatic way, and is related to the Unruh idea that accelerated observers, which has this boost operator as a Hamiltonian, will see the state they will see is a thermal one with some temperature, which depends on the distance to the boundary. So once we know this, the proof is very simple, because it's just writing the relative entropy with this information here, and what we get after a little algebra is just the expression of the Bekenstein bound. And as relative entropy is always positive, we have the proof there. So the conclusion is that the quantum Bekenstein bound holds. The original classical form of the Bekenstein bound is saved by quantum effects. It is consistent with black hole thermodynamics, with the original experiment, but it follows already from quantum field theory, that is quantum mechanics and relativity, and is not a new constraint coming from black hole physics. So let me then change to the second application, which is C theorems in two dimensions and 3 dimensions. C theorem states generally that there is a dimensionless function that is well defined on the space of quantum field theories, which decreases monotonically from the ultraviolet fixed point to the infrared fixed point along the normalization group trajectories. So it is a general constraint on the normalization group, and it gives an ordering of the conformal fixed points. The original proof of the C theorem was by Samologico in '86 for 2-dimensional theories, and we have a recent proof by Komardowski and Schwimmer for 4 dimensions. These proofs do not use entanglement entropy, but just usual positivity in quantum field theory. It was conjectured in 2+1 dimensions by Meyer and Sinha studying holographic C theorems, where the quantity that plays the role of the C is the constant term of the entropy on a circle, of the vacuum entropy in a circle. And independently, it was conjectured by Jaferis, Klebanov, Pufu, and Safi in 2011, based on a large number of explicit calculations for interacting theories, that the quantity relevant to the C theorem in 3 dimensions is the free energy on a 3-sphere, of the conformal field theory in a 3-sphere. In fact, these 2 versions of the theorem can be related because we know that doing conformal transformations, we know that the constant term on the entropy of a circle coincides with the constant term on the free energy on a 3-sphere for conformal field theories. So in order to show how is the proof of these 3 theorems on 2 dimensions and 3 dimensions using entanglement entropy, we need strong subadditivity, which is this geometric property I talked about. And we also need this other property of entanglement entropy in quantum field theory, which can be called causality, that if we have 2 regions which have the same, 2 spatial regions, we have the same domain of dependence, then the entanglement entropy in these 2 regions must be the same because of unitarity of the causal evolution here. Or one can express the same thing saying that both of entanglement entropies come from tracing over the global state over the same degrees of freedom outside. So in order to show how this is proved for 1 dimensions, one can take the strong subadditivity inequality in the simplest case of two intervals A and B, which are, however, boosted to each other. This is in a work with Marina Huerta in 2004. And using this, I don't want to enter into the details, but using this causality relation, one can show that what plays the role of A intersection B is, in fact, this interval that crosses between these two endpoints of the intervals, and the union is given by this other interval here. So the strong subadditivity here is just in terms of entropies of single interval. So it's a relation between the entropy for different sizes of the interval. And one can take this simple inequality and using the geometry of Minkowski space, one gets that this quantity, that is the size of the interval times the derivative of the entropy on the interval, is decreasing with size. So, and it's also well defined because entanglement entropy in 2 dimensions has only a logarithmic divergence that is killed by the derivative here. For small regions, we have the ultraviolet C, and for large regions, we expect to have the infrared C. And this is order because of decreasing property. And but we have also a general expression of entanglement entropy for the fixed points, which is given by this logarithmic term here. And just plugging in this formula, we get that the C for the fixed points is proportional to the Virasoro central charge divided by 3. So this proves the same theorem of Samologikov, the same theorem of Samologikov in a different way, and in fact, the interpolation function, outside the conformal fixed points is very different. For example, here I have the Samologikov functions for free fermion and scalar, and these are the C functions. One can play the same trick in 2+1 dimensions. Now we need an entropy that depends on only one size. For example, the simplest and most natural choice is a circle. And we have the strong subadditivity inequality between circles, but now we have to use many circles and take the limit of infinitely many rotated circles in order to get as intersections and unions in the strong subadditivity inequality something converging to a circle. There is also the problem that in 2+1 dimension, the vertices here, if I put these circles on a plane, will lead to ultraviolet divergence, logarithmic divergence that will spoil the inequalities. So one can avoid this problem just putting the circles, boosted circles, on a null cone, and then taking the limit of infinitely many circles to obtain circles in the both sides of the inequality. Again, just plugging the geometry of Minkowski space on these geometric inequalities, one obtains this thing, that this quantity that depends on the radius of the circle, which is a combination of the entropy on the circle and the derivative, first derivative of the entropy on the circle, is always decreasing. And at the fixed points, we expect that the entanglement entropy of a circle has an area term and has a constant term, only these two terms. So if we plug this formula here, we get that the C0 quantity that is decreasing at the fixed point is given by this constant term in the entanglement entropy of a circle. So this quantity can also, as I mentioned, can be mapped to the free energy of the conformal fixed point on a 3-sphere. That is why this theorem is also called as F theorem. So the conclusion is that there is a C theorem in 2+1 dimension for relativistic theories, also called F theorem. And up to now, there is no proof that does not involve entanglement entropy. Well, my final comments are these comments that somehow related to the usual ideas related to C theorems. One is that the C theorem somehow measure, the C quantity measures the number of the field degrees of freedom that, that are lost from the ultraviolet to the infrared when one traces out massive modes, let's say. But C is not an anomaly in 3 dimensions, but it's just a small piece of a very large divergent entanglement entropy. And in fact, it's very different from the number of field degrees of freedom. In topological theories, we have there is a contribution by the topological entanglement entropy to this C quantity. So even if there are no local degrees of freedom, this C quantity has some value that can be very large. So C does measure some form of entanglement, but as it's a small piece on a large entanglement, we don't know really what kind of entanglement it is. And well, my last comment is that somehow the relation between C theorem and some entropy can lead us to think if there is an information loss interpretation because of tracing of degrees of freedom when one does renormalization group transformations. But up to now, there is, even if there is a proof using entropies, there is no interpretation in these terms. And understanding this can be very important because it will tell us whether the C theorems are really something particular to the relativistic theories, or there is some version that extend outside relativistic theories. And finally, in order to prove the C theory in higher dimensions, higher than 3, using entanglement entropy, it seems that more inequalities are needed because with just a strong subadditivity, we only get second derivatives of the entropy, and then we cannot eliminate all the ambiguities in the entropy due to the larger number of ultraviolet divergent pieces that it has. So more inequalities seem to be needed, and this could be very interesting if, because nobody knows such inequalities. Thank you.
It's time for a couple of questions. Oh, Igor.
Yeah, I thought that the F theorem in this form does not apply in non-relativistic case. Like, for example, for the Fermi surface, this logarithmic term.
At least the proof does not apply, right?
Yeah, I thought I thought this standard form for the Fermi gas gave flow in the wrong direction. The logarithmic term,
yes. Yeah. So.
But even the homologic of C theorem does not really apply to non-relativistic.
Yeah, I was thinking more not to put an state somehow, but some other because people in condensed matter have applied this C theorem to situations where they don't know if there is interpolating theory that is always relativistic between the fixed points somehow.
Right. Any more questions?
Is there a refinement of the C theorem in the context of 2 dimensions that you can use entropic C theorem? So in the context of n equal to 2 in 2 dimensions, we know that there's this refinement of Zamolodchikov's theorem where the C function is replaced by a vector of charges of Ramon charges, R charges of Ramon states, and all of them monotonically decrease. Can that be derived using the entropic C theorem? And if so, are there generalizations of that in higher dimensions?
I don't know the answer to this question. In fact, in principle, it can be the case that there are many other quantities that decrease along the normalization group, especially if one puts some more information on what is the subset of theories that one is considering, but I really don't know how to.
Thank you.
Any more questions? If not, let's thank all the speakers.